Hello. The final project for our machine learning project is about self-driving car. And I'm Siqi Zhang. I'm a junior majoring in data science.
I'm Charlie. I'm a sophomore majoring honors math.
So the topic is about a self-driving car using convolutional neural network. So our objective is to build a model to learn the image of the road situation and then output the driving command of four commands. The first is the steering command. The steering is the angle the car is about to turn. And the throttle is the acceleration. And then the speed. And the last one is the brake. Is the how much strength we use to press the brake. It's like a gently brake or a strong brake. So in a word, our model mainly will input an image and then output four continuous numbers about the driving commands. So we'll first talk about the data pre-processing we have done, and then describe the details of the convolutional neural network, and then give the interpretation of the results we got.
So I'm gonna follow up and talk about the data pre-processing. So we got our data from Kaggle, and we have put the address of our datasets here. So basically, our data are 8,000 and 8,036 images, which are of size 160 times 320 times 3 because they're RGB pictures. Also, we have the output. Our output are four labels, which are four continuing numbers, and they signify the driving commands of steering, throttle, brake, and speed. And the data actually also provides us with the left view and right view images, but we didn't use those pictures at last um, because the time is limited. So for the first part, we did the resize of our images because we firstly tried feeding our data into the model without resizing the images, and it turned out that the training was extremely slow and we couldn't get our desired output. So we used the package CV2 to resize the images from 160 times 320 to 32 times 64, and we have also attached our codes here. So we then follow up and divide our data into three sets, which are training set, validation set, and test set. So in training set, we have 5,063 images, and in validation set, we have 562 images, and for test set, we have 2,411 images, which are like 30% of our total images. And we are also put our codes for separating the data here. So I'm gonna then talk about the CNN model that we used. So for CNN model, we have two convolutional layers, two pooling layers, and two fully connected layers. And we use the activation function ReLU. So in terms of other details about our model, we have used the loss function MSE because the output for our model is real numbers, and they're not for classification. So it's not possible to use cross entropy loss for this model. And we have used the atom optimizer, and also we used mini batch gradient descent with batch size 64. In addition, since our model has the tendency of overfitting the training sets after iterating for 40 times. We decided to use a early stopping regularization, and we stopped right after 40 iterations. So I'm gonna now present the result and conclusion to you. So the graph, so this is the graph of our loss and validation loss. As you guys can see, um, they both go down dramatically after iterating for 15 to 20 times. And since we have no accuracy for this problem, we calculated the average differences from between the predicted data that we got from our model with the actual data in the data sets. And we have listed it here. As you guys can see, all of them are in a comparatively small range. So we can assume that our model actually successfully predicted the right speed, throttle, steering, and brake. So Siqi will follow up and talk about the future work that we could be doing.
So if we have more time, we may want to add the L2 regularization because this will take much longer to train the model. And we may also want to collect more data and to train on more data to see whether this could improve our model. We can also do data augmentation to get more data. And also, we could also try to use a more powerful network structure and do some transfer learning to further improve the model. And that's all. Thank you.
Thank you.